All right, in this next video in section 13.2, we're going to look at finding the domain of some multivariable functions. So in the intro video, we saw that the domain of a function of two variables was a subset of the xy plane. Okay, so with that in mind, let's look at part A. We have f of xy is 5 minus x minus y. Okay, so notice here that the right-hand side is linear in both x and y. So for this reason, we're going to call this a linear function. And to find the domain of a function, whether it's single variable or multivariable, you want to ask, can something go wrong? Is there some kind of restriction maybe that we need to make? So things like division by zero or like a negative under a square root, that sort of thing, right? Well, here for this function, any input we feed it, right, any x and any y, this right-hand side is going to know what to do with it, right? In other words, this will always produce a nice, real-valued, well-defined output. Okay, so for that reason, we would just say that our domain is all of the xy plane, all of R2 here. And so to draw this as a set in the xy plane, here we're simply saying that, well, any point you choose in the plane, right, will serve as a valid input to this thing, because again, this right-hand side will always produce a well-defined output. Okay, all right, great. So now let's go ahead and check out part B. We have g of xy is the square root of 9 minus x squared minus y squared. Okay, so now here I'm going to be on high alert since I see a square root, right? If this thing is going to be real valued, right, we need 9 minus x squared minus y squared to be greater than or equal to 0. So this is equivalent to saying that x squared plus y squared has to be less than or equal to 9. So what is this describing? Well, if x squared plus y squared were equal to 9, that would just be a circle of radius 3. And then since we have our inequality here, that's a less than or equal to. Okay, this is saying, all right, for the domain, we are going to take all points on that circle and everything in its interior. Okay, so this would be a picture of our domain. And as a set, okay, I can write it as the set of all ordered pairs x, y, so the set of all points in the xy plane such that x squared plus y squared is less than or equal to 9. Okay, great. All right, pressing on. Let's check out C. Now here we have h of xy is equal to 1 over the square root of the quantity x squared plus y squared minus 4. And now here there's really two things to watch out for, right? There's the square root. So we're going to need this thing inside the square root to be greater than or equal to 0 for that thing to be real valued. But then also because of the division, I can't have the thing inside the square root equal 0. So putting those conditions together is going to say we would need x squared plus y squared minus 4 to be strictly greater than 0. Okay, now this is equivalent to saying that x squared plus y squared is going to be strictly greater than 4. So what is this describing? Well, if x squared plus y squared were equal to 4, that would be a circle of radius 2. But since, notice, this inequality is strict, I drew that circle as a dashed line. Okay, so this is a circle of radius 2 centered at the origin, but it's dashed, meaning we're not actually including points on the circle itself here. And then, since the inequality is a strictly greater than here, we now want all points in the exterior of this circle. Okay, so everything out here then would be included in our domain. And we could write the domain as a set in much the same way we did for part B. It'd be the set of all ordered pairs xy such that x squared plus y squared is strictly greater than 4. Okay, there would be our domain. Okay, great. And then one more here. This is part D. F of xy is equal to the log of the quantity x squared minus y. Okay, so now here the thing to watch out for with logarithms is that the input here, in this case it's x squared minus y, this has to be strictly greater than 0. Okay, can't feed a logarithm 0 or something negative, right? And so now what is this equivalent to? This is equivalent to saying that y has to be strictly less than x squared. All right, so what is this describing? Well, if y was equal to x squared, that would just be our standard parabola, right? And so then, and again, notice I drew that as a dashed curve there. I'm not including points on the parabola itself. And then since y is less than, that's indicating we should be shading everything below the parabola. Okay, so this would be our domain. And in set notation, we'd be looking at the set of all ordered pairs xy such that, well, y has to be less, strictly less that is, than x squared. Okay, great. So now what I'd like to do before we finish here, let's go ahead and look at a couple graphs of these surfaces and get a better feel for how that all is connected to the domains we just found. So here is our first surface. Notice, right, this thing is just a nice plane, right? And we said here, right, that this is a linear function of two variables, x and y. Well, linear functions of a single variable are just, right, nice straight lines in the xy plane. Well, in the case of a function of two variables, linear functions are just planes in three-dimensional space. Okay, and of course, no restrictions required there for the domain. All right, moving on to part B, we see this kind of thing. Now here, I'm going to go ahead and rotate over here like this. Notice you see this circle of radius 3 here, and I'm seeing surface, right, on that circle and in everything on its interior, right? There's the bottom side. Now you might well ask, what's going on with this weird jagged portion of the surface? Well, what's happening there is that the software just struggles with the boundary portion of the domain, and that's really typical of really any kind of software like this. So if you use like Mathematica or any other graphing software, so like for example, here's the what Mathematica would spit out for, this is actually the graph for part C, but the point being, yeah, it's just spitting out some weird sort of jaggedness. Now this thing you might suspect, it looks kind of like, the top of a dome, like maybe like a hemisphere. If we go back to part B, that is in fact the case, and let's make a little note down here of why that is. So here, okay, g of xy is the square root of 9 minus x squared minus y squared. So in other words, z is the positive square root of 9 minus x squared minus y squared. And since z is the positive square root, z is always greater than or equal to 0. That's why we're only seeing the top half of the sphere. And now squaring both sides and rearranging, this is saying we have x squared plus y squared plus z squared is equal to 9. And again, z is greater than or equal to 0. So this is really just describing a hemisphere. Okay, if you watch the distances and spheres video that I've posted, you would recognize this as the equation of a sphere of radius 3, because this right-hand side is the square of the radius, whose center is at the origin. Okay, so since, again, because of the positive square root there, we're just getting the top half of that sphere, so this nice hemisphere. All right, great. So anyways, going on now to the next surface, we're seeing this thing, right? Again, weird jagged behavior on the boundary. But again, the thing I want to really highlight here is, right, you see that circle of radius 2, and we're seeing surface now on the exterior of that circle, right? And notice, because of the division, if we edge really close up to this boundary, the denominator is going to get infinitely small, and so that's why we're going to see this blow up happen. This asymptotic behavior is what we're seeing there near the boundary. Okay, so that would be part C. And then the last one, this is pretty cool. So here's the surface. Again, we see some weird behavior around the boundary. Now, what is the boundary? Well, I'm going to take this look right here. Right, we said, is everything below this parabola y equals x squared? And you can see there's that parabolic cutout there, and we're seeing surface right above that region, right, that falls below the parabola. Now, as far as the behavior near the boundary, right, when you work with log, and notice, by the way, this math3d.org, it likes log for natural log. So if you type in ln, it won't know what that is. So for working with logarithms, right, if you input things that are really, really small and positive, right, which is what we would get if we were to inch closer and closer to the boundary, the output becomes infinitely large and negative. And so that's why you see this sort of bizarre looking descent into the abyss, so to speak. So, but yeah, pretty interesting looking surface there. And we're going to go ahead and stop there. I'll see you next time.